Forces, that was a key word. Yesterday we got a formula that could tell us the force between two charges, or maybe more than two charges, depending on the total force. And that was given as that. Okay? So, now we're talking about electric fields. Is there an electric field? Well, if I said magnetic field, do you got a kind of mental image, visual going through your head? Have you seen the field lines before for magnetism? You know that's a force, but it's a non-contact force. It's kind of like gravity, right? You bring positive charges together magnetically and they will repel. If they're unlike charges, you get the north and the south pole, then they'll attract. There's field lines, and the same thing with an electric field. For any electric field, E is F over Q. That kind of looks like this, doesn't it? But it's different. So we can use this to measure the strength of the E field or electric field one more? Yeah. By placing some what we call a test charge, QT. And measure the force. So there's one formula with an E in it. For a single point charge, the electric field my hand wants to go faster than my brain will allow. Substitute that in for F in this. So what do we got? E is F K Q Q over R squared, and then I got 1 over Q, and one of those Q's is Q1, the other one's Q2, so this guy is going to be one of the two. Okay, and what happens? Well, one of the Q's cancels out. So there's another formula. Electric field is K Q over R squared. Okay? So, just got to look at what you got. If we got a force and we're not talking about an electric field, then I guess I want to use that one. If I got a point charge and a distance, well, I guess I want to use that guy. Okay? So, a couple of things you got to stick in your head. Because these are given on your formula sheet. You just got to know how to work with it. Electric field charge. You remember in kinematics, and we talking about acceleration and like how do we take up or down? One books do this way, and A is going to be positive down. And other books say A is negative down. We took it as negative down. It's just a matter of convention. What are you going to do? Well, same thing with electric field. We took the convention as the direction is where a positive charge would go. You'll know what I'm talking about when I show you a picture. Okay, so that is the direction. And then drawing some of these electric fields, something else you got to remember, and if you do, it's easy marks. They never cross. Like lines of magnetism, they will never cross one another. They're all unique. Kind of like a parabola. Okay, so let's look at a couple of pictures. E-field lines. They look like vectors. If there's a point charge, well, what do you think? Would that charge be positive or negative? I'm not putting a plus or a minus on there. You got to know from the electric field lines. How do we know it's negative? Because the lines indicate where a positive charge would go. And if a positive charge would go like that, well, that's showing attraction. So this guy must be negative. Okay? So that's all you're going to get is a little picture like that. You got to, these two things I'm telling you, you got to know them. Got to stick them in your head. Here's point charge, there's point charge. And these look like lines of magnetism. Okay, but these never cross. And it goes out like that, will go like that. So it kind of looks like a magnet. You've seen something that looks like that before, right? Or maybe that's a battery. Don't draw this. Okay, one pole negative, one pole positive. So this kind of, and I drew it kind of quickly, but it's symmetrical. Which indicates what? These guys would have equal charge strength. If they don't, you get a different picture. These aren't going to be symmetrical. By the way, are you able to tell which one is positive and which one is negative? The one on the left, what's the charge on it? Sure, yeah, because the lines are going away from it. We can tell by those arrows over there. And that guy's a negative. Okay? Whereas if we got this, Okay? Not symmetrical. So those are unequal strengths. This is a little tougher. Which one is stronger? The charge on the left or the charge on the right? It's kind of like sucking everything into it, isn't it? Right? Not as intuitive. But this guy, he wants to get repelled from that. But as soon as he's repelled from this guy, he's feeling pull from this guy way over here, right? So this thing is, once it's remember this is the square of the distance. This is r squared, right? So every double the length is only a quarter times the force. Once he's far enough away from him, he doesn't keep going that way, because this guy's so strong, he's going to suck him way back over there. So this guy's quite a bit stronger. Okay? That's a negative, 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 negative. This guy's just a plus, a single one. So opposite charges, but this guy maybe is about 4 times as strong. Okay? Example. What is the magnitude of the E field at point P? Yeah. Right? That so E field, E is F over Q, or E is K Q over R squared. Which one do I want to use? Yeah, do I have the force here? Doesn't say it, doesn't give it, and I got a distance, right? So what's K? 9 times 10 to the 9. Don't have to memorize it, I'll give it to you. This is 3 times 10 to the minus 6 coulombs. R, 0.03 squared, okay? It's as simple as they come. Put that in. And that's 3 times 10 to the 5. What's the units for electric field? I don't think I gave that to you. Newtons per coulomb. You're thinking E for energy, right? So I should have put that up here. So remember, that was the same as force, only I canceled out a Q. That's why I got a C down there. Okay, one more. Let's look at some components. What does that funny abbreviation say? Positive. Five meters north of P. A negative charge. Guess that's redundant if I got a sign in there, isn't it? Is 4 meters west of P. What is the magnitude, meaning we don't need a vector for direction here, of the electric field at P? So there's P. Something 5 meters north of it is that charge, positive, and a negative charge is 4 meters west of it. Okay? So analyze both of these things. What's going on between these two? What's the magnitude of the field at point P? What does this guy want to do to it? Yeah. Okay, he wants to make it go that way. And this guy, what does P want to do as far as this negative charge is concerned? He wants to go that way. He's attracted to that one. Okay? So we've got that due to this one. We've got that due to that one, and it doesn't matter. You can draw them like that too, but the resultant in both cases is like that. Okay? But I don't care about the direction. I just want the magnitude. Well, what is this one here? We've got K, Q over R squared due to that guy, which is 9 times 10 to the 9. Charge is 3.2 times 10 to the minus 4 over the distance, 5 squared, which is 1.15 times 10 to the 5, and if you want a direction, it's south. Okay, this guy, again, same formula. 9 times 10 to the 9, this charge. Again, the signs don't really mean much. We know what the direction is, right? So don't even worry about the negative. Over 4 squared, and that guy is, what did I get, 1.58 times 10 to the 5 also. Okay, so this is a right angle. One's south, one's west. We just want a magnitude. I didn't really even need my picture. That squared and that squared. Take the square root of that, and that's the magnitude. .95 times 10 to the 5. What's the units for E? Newtons per coulomb. Okay? So this sheet I'm going to give you is 2 days worth of stuff. Okay, do half of it. You should be able to do up to 9, I think. So if you want to do 1 to 8-ish, you'll be good. There's only about 3 or 4 after that. You want to do 9? Be my guest. Got another example for, I think, the last 2 or 3 tomorrow.